Financial securities with dynamical systems. The left part and the right part, in some sense, can be more different. So the right part is what we're all familiar with. These are our LTI systems. We can analyze them, we can implement them, we can control them, we can simulate them on simulators, we can build stuff with them. This is the workhorse of every control engineer. On the left side, you get financial securities. You can take a course in finance and they'll teach you about Black-Scholes. And it's also a differential equation, but not in time. It's a complicated differential equation. It's not a linear differential equation. It's only one instead of an A matrix and all of that. It's just very different. Okay, it's very different to understand, very different to see what it is, the commonalities. And the way these differential equations work is as a big disadvantage. We don't know how to control them. So if you do a portfolio with it, we wouldn't know how to build a controller with it. We wouldn't be able to analyze them. We wouldn't be able to go to the Laplace domain. We wouldn't be able to simulate them. Well, some finance people do simulations, but they run very slow. All right, we have no insight in why this thing is like it. So what I want to do with this talk is show you how you can value its portfolios and financial securities using good old dynamical systems theory. That's the goal of this talk. Now, how did I get that? And I have summarized this here in this little circle. So I started off as a systems and control mechanical engineer a long time ago. This place was called the Technische Hogeschool, so we weren't at the university yet. And then I did my master's in controls, and I kept doing controls, but I got more and more interested in stochastic control. And this was my specialty also at MIT, where I did a PhD. And then I did some thesis that was theoretically interesting, practically don't sell, but nobody cared. So based on that, I got a job at a different job office, and I ended up going to Berkeley to the Operations Research Department in Industrial Engineering. And there I further developed these models in the context of decision theory, utility theory, and how we can apply that to engineering systems. And then I left academia with the idea. Anders blijft het maar liggen.
Ja, maar ik klik op de audio dingen ook.
Ja, moet je dit ook maar uitknippen.
Zo, on the to-do-lijst.
Ja, maar hij... The idea was to take all this, and I left academia, and this stands for Wall Street. I was going to trade stock, and at that time, I had to believe that all these ideas would help me do that. Well, that was a wrong idea, and I was a miserable fool for thinking that it would, it turned out. But it did all work out for me in another way, and perhaps I should have known that finance is like love and war. Only simple strategies work. So that's what we did, and then I retired, and I did nothing, and now I've been back at the TU for, I think it's approximately 9 years or something, trying to put this together. And a simple strategy to me, which works, is dynamical systems. At least for a system and control guy, that's a simple strategy. Just have a linear model. All right? So in principle, that has the potential of being applicable to it. Okay, so that's what I want to sketch in this talk, is how we can do that. And then solve this problem of life that I had, now, if I can say it dramatically, namely that what use was all this stuff when I just have to use an Excel sheet and my thumb in order to do this, okay? Yeah. possible to. So there's going to be, what I'm going to do is I'm going to show you three different, the analog of three different approaches to valuation that are current in finance. And I have them at the back, so let me just quickly go to the back here. In finance, typically we think about this layer here, the Black-Scholes and all these models, and that would be, we'll see that a little bit later, that will be, is analogous of energy methods, and in particular it will be the Hamilton-Jacobi equation. I'm going to start down here. They use something called stochastic calculus. Ito calculus is another name for it. This is analogous to our equation of motion and approach for dynamic systems. And then all the way at the top, some more theoretical types, they'll be talking about utility approaches, how much utility is in there. And we'll see that that's very related to quantum mechanics and the Schrödinger equation. So it's kind of a wild ride. But why do we have to do all this? Well, the reason is that if I first show you how this works, what does that have to do with any of this? How do you know that even solves a valuation problem that's formulated in this Black-Scholes thing? And you already know that if you understand the connection between these layers. Now, we're fortunate that in mechanics we have a similar situation. We have just a regular x dot is ax plus bu approach, and then we have the Hamilton-Jacobi approach. And then on top of that, and we may not do that in this faculty, but there is a more quantum mechanical, a wave mechanical approach to it. Okay, so what we see is these different economic approaches. In finance, these approaches will have their analog in mechanics. Okay, let's go back to the work itself. And I want to juxtapose these LTI systems with what they call Ito calculus or stochastic calculus. Now, what a finance type might write down is this kind of what he calls a stochastic differential equation. Most of you may have seen this. And they have some variable x. They typically don't even say what it is. They don't bother with the units. This could be a price. That could also be, I don't know, volume or stock of something. Mostly this is a price. And then this t means that it depends on it. And then a change in this price, it depends on time itself, plus some factor that's still totally random. And this is what they would, this is the Brownian motion. And the way they model it, they have these two parameters. They have this drift thing that depends on t, and somehow this dropped out of it. I just copied this from Wikipedia, and this t here dropped out, but this volatility can also depend on t. Now, what's the problem with this for applications? Well, one of the problems you'll find is that these are quite abstract parameters, this mu and this sigma. The sigma they call volatility. How do you measure that? So, several things. I think it does. Traditionally, it will be done by fitting it to past data. But how do you get the time dependence in there? What if the past data, as they say on Wall Street, is no predictor of the future? Now, why would this be relevant? And then even if you did that, what does it represent? Okay. There seems to be no operational definition for these. In the same way you can define what a mass is or a spring constant. Then there is this drift, a similar thing. It somehow depends on t, and somehow you get a drift. And what does it depend on? How do you know you fit it? And people actually make money with this. That seem to work. All these models that seem to work, they work until they don't work anymore. So many more people went bankrupt. In the end, everybody went bankrupt using this. And then they have to adjust it, they have to tinker with it, and that's where we stand now. Another way of measuring this sigma parameter is to assume a model like Black-Scholes is true, and then if it's true, calculate what this sigma should be, and then plug it in. Now, that's like assuming your LTI model is true, and then when you get wrong data, you just, this is how you define match. You don't go separately to match. They call that implied false. So from an engineering perspective, there are big problems here. The other big problem is that everything is thrown in here and here. There's no further structure, like an LTI model, it will be multiple order. You can have a, indoor system, I don't know, and everything is, is very complicated. And it's just in this one equation, and these parameters, they just have to deal with everything. Yep. So these are things that you can look at and say, well, it's abstract, it's at the same time limited. Now, how do we get out of this? So one way to look at this that is different is say, all right, what we can see is this drift somehow captures the deterministic part. This is how it goes in time, because this is the dt part. You can make some kind of dynamical system out of this. And this part is something else. It's what is not deterministic, the random. Okay? So take that as an approach and say, well, okay, maybe our deterministic models, they sit here, and the stochastic part sits there. Okay, now if we do that, then what we do, and what we always do, we go back to a simple second order system, or let's the mass spring damper system. And you know what? I'm going to make it even more simple. I'm going to throw out the spring. I'm just going to look at a damper. And that's the first order system. I'm going to see if I can do something with this equation, just using the mechanics of this system. Now, this damper is kind of complicated here. I'll explain this later, but just imagine here a damper, then you all know that this is the equation of motion, and just forget about this. Okay? So here is the force of demand. This is the demand of electricity. This is the derivative of the flow, right? This is the extension of the demand. Here is the friction. Here's an exogenous incentive. And here there's fluctuating incentive. So in a sense, this is all the drift here, and this is somehow this Brownian motion. Okay. Now this equation has a name, and it's called the Langevin equation after its person who formulated it. And how did he do this? And he just wrote it down because that's what he observed. This was resolved by Einstein, who kind of figured out what's going on. So for a long time, you see, the whole thing of this Brownian motion, it started with this botanist, this Brown, and he looked through his microscope, and he saw that a pollen was just like drifting around. That's what this thing's called, a drift, it's just moving around in a fluid. And he was a clever person, and he ascertained that it couldn't be an animal. First, somebody says there must be some animal, because how the heck is something just moving around? It wasn't an animal. So he said, well, this is a problem. So how can a particle move around? There must be some random force acting on it every time doing something. I don't really know where it comes from, but whatever. Maybe it's like gravity. I don't really know where it comes from. This is the 19th century. I think it's maybe even the beginning of the 20th, but 19th century. They didn't really bother where it would come from. They just knew there had to be a force because Newton had told them that for every motion. So he added on this force that is the fluctuating force that causes these fluctuations and ultimately this drift. Okay? But for a long time, people just didn't know why it was there. And then Einstein, he came along, and then among a few other things he did, and he explained where this came from. And this is where it comes from. So in mechanics, you would look at this damper and go like, okay, this is a bath boil, there's this plunger going through. All it's doing is the kinetic energy that's in the mass gets transferred in here, but by pressing the oil particles through this little hole you got here, they're going to go every which way. All right? So you have a motion of one big particle in this direction that gets transformed in the motion of many particles going in many directions. Okay, that's what's happening. So it's an interesting point of view because Joule had already said that kinetic energy would have to be conserved, and here Einstein was able to explain what's really happening here is that kinetic energy is in a sense not conserved, but only directed kinetic energy. So what what gets translated into is kinetic energy that's going every which way. All right? That's the process of damping. I think I'm using Einstein. I should use Boltzmann's name. He is the guy who did that. And Einstein came later and did the fluctuation part. So please, cycle back in your head in this recording and put Boltzmann for this explanation. All right? So Boltzmann said, well, this process, how do I measure how much of this directed kinetic energy is distributed every which way? So he needed a new variable to do that. Huh? And that variable Clausius already put down, and he called it entropy, but he didn't know what it was. He just realized there had to be something like entropy that was increasing because this thing was going, what's happening. And then Boltzmann, he had the idea of describing this kind of distributing out of the kinetic energy as that's the variable that measures that. That's full nature. First picture, you know that. So if something is hot and I put my finger on it, it feels hot, but what is that really? That's all these molecules like banging against my hand. Now, when Boltzmann was looking at this, he assumed you have something like a mole of gas. I don't know how much a mole is. I think it's 10 to the 23 or something ridiculous. All right? So that's what you would call the thermodynamic limit. All right. Now let's translate that to economics. And then, I want to do one more thing. And then Einstein comes and says, okay, this is, so this average behavior done by this force, that's the friction force, and that goes in there. So that thing is just deterministic, okay? So that can be shoveled into this thing. So you got to see that. Right now, we have a bunch of stuff randomly, but the net result on the average of all these things banging on there, making it difficult to push that plunger through there, okay? That is a deterministic result, okay? Okay? That's this term here. So this goes with dt. That's what I call something deterministic, when it goes with dt and you can write a differential equation. But now imagine, and this is what Einstein did, that you don't have a mole in there. You have 20 billion balls bouncing around. Okay? So you push this thing in, but now this averaging will still occur. However, even if you leave the piston alone, it will start banging up. It will move up and down because once in a while a ball will hit it. On the average, of course, it will be hard to put it in. But once at the same time, you're getting all this shaking around, right? And the amount of shaking will reduce as you increase the number of balls there. All right? So by measuring the amount of shaking, Einstein was able to determine what Avogadro's constant is, how many atoms there are in a ball or whatever, okay? And in doing so, he established the economic molecular theory. I mean, a lot of people did not believe that there might be molecules. And through this reasoning and these experiments, Einstein said, this is a big achievement, okay? All right, so this is the background in mechanics. You all know this, right? Maybe you don't know the fluctuation part, but it all makes sense. I'm going to translate that to finance and economics, okay? We know what this is. This is demand, right? Then we know what this kinetic energy is. That is the surplus, all right? Which surplus? Well, the surplus in one particular type of goods, okay? In this direction. Okay, these are all apples. Okay? Well, they're all finance and business, they're all money, right? All time. Okay? Now, what happens here is you have all these, this is a big guy, and these are tons of small guys. It's like a market. Right? This big guy sort of dump all this stuff in the market. So the market gives them a force back, which is the market friction, right? Transactional friction. That's just average what he's going to pay when he does tons of interactions with all these little people. So you go with your big your big lot on the stock exchange, and you dump it all in there, and you see everybody gets excited, all the market makers, and they start, now, you go through all the bids that are in the, what is it, the order book, everybody's trading with you, the price goes up, blah, 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 right? Huh? Okay. But now, so what do these traders do with it? Well, they acquire some of this, but they don't just acquire that. They buy other stocks with it to hedge their positions or do this. So now, what you get is that the demand in this direction only distributes over two other directions. Okay, so people at first buy apples and then maybe also pears, bananas, and you see that because they take one apple and they buy a banana with it, right? They just start exchanging the stuff among each other, and they start. That's what we call distribution. So we distribute the surplus among the different agents, okay, and we diversify. So we say we only have apples, but I want to have a diversified basket of fruit, So I'm going to get some bananas. I'm going to get some oranges, So that's what's happening, all right? So entropy in this case, what it's doing is measuring is a degree of how diversified the portfolio is. So if these are shares with one stock that you have because you sold your company or you have a lot, you start selling it and people start buying other stocks with it, okay, then you're diversifying your portfolio. Okay, so it's a measure for the degree of diversification. At the same time, it's also a measure of how distributed it is. But if this is, say, only the transactions in between two people, or use a few balls, but lots of stocks, then okay. So it's a product of the number of traders and the number of stocks that we trade. Now, if you look at, say, the New York Stock Exchange, then there's the S&P 500 is the 500 most active stocks that everybody looks at. That's not close to Abraham's number. Okay, 23, right? There's 10 to 2. All right, now there's a bunch of traders. There's not 10 to the 21 traders out there. Don't even have that many people to live, right? Not even close. So you can see in a practical finance application, it's really hard to get a mole of options, running around here. In physics, the dimensions are of course only 3, and it's not totally true. You can make complicated systems of higher dimensions. But say if these are just particles in dimensions 3, and we can have 500 dimensions, but still doesn't really, the product of a number of dimensions times the number of agents is never going to be close. So you're going to see quite a bit of fluctuations. Okay? That's the origin of the fluctuations. So this is that extra incentive that you got to add in here because the market is not perfect. It's not totally homogeneous everywhere, and you're just going to see a lot of price action because of the bid-ask spread. You're bumping in between these things, and because the liquidity is not always. Often they measure this with liquidity, right? Okay. So what we did here is we really zoomed in to the working of this damper, and we gave it an economic interpretation. And you see how you can now use this thing, okay, to do this kind of thing. Now, what is the great thing about Einstein now? And now I'm really saying Einstein. He was able to calculate the magnitude of this force here, this incentive. And he reasons that it had to be equal to this expression. So 2 times the damping constant. If you don't like that, put the discount rate here and multiply the inelasticity, all right, times the temperature, okay? And that's the factor that goes in front of the white Gaussian noise. Okay, so whereas the sigma here is an abstract quantity that you don't know how to measure, here, this thing we know, this thing we should be able to. So our task is to give this thing a good economic meaning. All right? If we do that, we got the whole thing under control. We can just put our riskometer instead of our thermometer, right? And we know how risky everybody considers it. Okay? We can make bond graphs. Now that interpretation is not very far off because there's two ways to look at it. The first thing is that the kinetic theory definition of temperature is, I think it's twice the average kinetic energy. Okay, I think there's a factor too. That's not important. So what's the average kinetic energy? Is the average surplus. So you got a lot of traders as just saying, what's the average surplus? What's the average profit everybody make? Average it, and that's it. Okay, that's one way to look at it. The other way to look at it is to say, well, how does the surplus get allocated here? All right. So how much of the surplus gets lost in this diversification process? That's the heat. Okay. Now you know what the degree of diversification is. So you can see how fast people are diversifying. Okay, so here's the heat. And you know how fast people are diversifying, right? As this. You go from this, you know, and this, you know. So if I define temperature to make this come out, this is the usual way you would do it in macro. Okay? So we know this. This is the rate of which we diversify, diversification. This is the surplus that's allocated to the market. And we define T. So this is sort of a definition, a little bit weird, but this is how you would formulate it in first year thermodynamics. Okay? And if you do that, then you know that the internal energy here, if I look at a change on that, you know, that's going to be the heat, and that's just TDS. All right. Look at some other stuff like expansion, stuff for work, that good stuff. Okay. That's probably the most interesting, the most simple way. Once you do that, you can make a bond graph. So here I've made a bond graph where I've connected this commodity market where this demand is to a risk market where this diversification flows. Okay. So all the bonds are the power. So that's the surplus, the rate at which the surplus gets allocated. Okay. So you know that this is an incentive. So this is the force of demand. This is just the flow. So this must also be a flow, or it's going to be the flow of that diversified, diversification, the rate at which you diversify, and this must be some incentive that belongs to it. Okay, so this tells you what this is. It's sort of the risk incentive. If this is the systematic risk, and this is an interpretation of risk where you call it systematic risk, where you say, I can't find it anymore, right? It's there, it's stuck in there, okay? So then you can see that T as well must be equal to. So I'm taking a regular bond graph, and normally what you would do is you would cut it off here, and all this stuff would just disappear, right? And that's what we call dissipation. And we would say mechanical energy is not conserved because we're losing it. Right? It's kind of an old-fashioned way of thinking about it. That's what these types did before they Joule did his experiment. They measured mechanical energy in horsepower. You know, the mechanical energy is what we would call the available surplus, what you can do stuff with it. okay? And they also had to eat something separate, this they would call calories. In a broader economic engineering, these calories are more, this is more like welfare. You feel good because you're well diversified. You don't have only water to drink, you have all this other stuff, okay? All right. And they were not connected. The heat would just come out of nowhere, and the mechanical energy that was possible would just disappear into nowhere. And Joule was the first to connect them and say, well, no, there's a law of conservation of energy. Now, in these bond graphs, what we do, we kind of don't keep track of it. Okay, so we just assume that the circuit board or building, there's just a cooler on it, and any heat that gets generated just gets dumped out, in the environment. And it's just not a closed system. But if you thought of it as a closed system, you would have to, you take that environment or whatever that cooling bath is and you put it in here. You'll have to keep track of all that entropy that you're dumping out, okay? And there's a new container here. Now, if this is all risk that you're moving across, or diversified surplus, which we could call that systematic risk, then you'll see that you can treat this as sort of an element, okay? So instead of an R element, you have some kind of transformer. In a bond graph, they call it an RS element. I'm not quite sure what the origin is. And then you dump in this entropy, this diversification, and it gives you back some kind of risk temperament, okay? So, of course, it gets hotter and hotter and hotter, so you're going to get more and more averse to taking on this risk. Okay, you want to cool down. So if you have a big guy like an insurance company who's quite cool, then you're going to be able to give you risk. You're going to have to pay something because there's going to be this insurance broker in between who's acting like some Carnot engine trying to get it out. All right. So that's the big change. This is then the relationship for that I element. It's just a regular demand line. And this would be the relationship of this thing if it was a perfect gas, right? So this will be the heat capacity, which you could call the risk capacity. Okay? It's a little bit different, but the principle is the same. So this is about the risk that you bear is here. And this is the demand that's sitting in here. So value. This one is a store of value. This is a store of risk. Now, there's this extra thing. There's one about these fluctuations. This just is fun. But the fluctuations, they're going to come back. And there is this factor here that turns out will be in the opposite direction. And you keep track of all the negative signs. I think I should have. It goes in the opposite direction. Okay, and that's what they call neg entropy. This is something that Schrödinger came up with. So if you think back on this experiment, what's happening? It's a little bit weird. You get told that entropy can only increase in the universe, but it's not quite true from this perspective, because suppose you just took this hot bath and it's got like 20 big balls in there, and you put this plunger in there, it's going to move. And that movement here can be rooted as kinetic energy. There is kinetic energy in there. So it's almost as if the first law of thermodynamics is broken, that all of a sudden you have no movement, and from heat you can get movement. Okay? You see? The reason this is okay is because the movement is on a different time scale. See, in the fluctuation you get out in a small dt interval, you can get infinite amount of ups and downs. So there's no way to predict what this thing is going to do. That's why we're going to call it random. It's physically impossible and mathematically impossible to make a model, the differential equation, with time that actually does that. You'll have to have something with square root of time and half derivatives, all kinds of stuff we can't measure, okay? So the entropy goes with time, and this thing goes at a faster rate. So really, it's still okay. All right? So there's a little bit of idiosyncratic risk that comes back, but it's kind of not usable. All right? Huh? That's what makes it okay in terms of the formulation of the second law. Schrödinger wrote a whole book about it. And I think Schrödinger was going to argue that all of life are these random fluctuations. There's all kinds of people who argue things. Okay. I actually don't come to the. This is just interesting to note, but I think for us, it behooves us to be a lot slightly more practical and say, well, it's just what you see in the market is these random motions, and you can't do much for that, you know. Huh? You can never really act on them because they always come when you don't expect them, you know, and they're gone before you can do anything, you know. So that's why they're truly random. So I'm calling this idiosyncratic risk. I'm not totally happy with the term because you would feel you can diversify that away, and in a sense, well, I am happy because in a sense you can diversify this away. If you just add, you know, more and more agents and go to the thermodynamic limit, it just goes away. Okay, so maybe I am. Okay, so it's possible to get rid of this just by diversifying, increasing the degrees of freedom, but it's not possible to get rid of this. That's what the second law says. So the second law of thermodynamics for economic systems is saying that the systematic risk has to keep increasing. Okay, society and any human interaction, in fact, is always reaching a state of maximum diversification. And so it's nice to see this picture of what's happening as a sort of formulation, very general formulation of Adam Smith's principle of the invincible hand. So Adam Smith, he had this idea that whatever happens, there's always this invincible hand that's pushing the market to equilibrium. Okay. And you can think of the second law as being that. Okay, so as you know from thermodynamics, here are the equilibrium states. So here's your internal energy, and here's your entropy, right? So this is the internal surplus. This is the degree of diversification. If you're here, you can just diversify yourself to this thing. You'll have this temperature, but this is your risk temperament, and then it's over. You can't go this way, right? You can take out some free energy, so that's some free surplus. You can take that out. That's what traders do, right? Or insurance brokers, you know, or you just kind of, and this is not insurance broker. They'll act between two things. You can take a system. But this is, if you leave it alone, what the market's going to do is do this, just go to equilibrium. All right, so you get the entropy death of the market. Of course, every time new stuff comes in, just like our sun, you know, new people are born, the economy goes on again. A new trade agreement, new trade barrier. Every time there's a big shock. All right. So you can make this bond graph. So you see now how you have this bond graph. You have to, it's a little bit more complicated because there are now two flows. So here I subtract the fluctuations from the actual flow, and here the fluctuating force from the actual force. It's a little bit more complex, but it all works out if you do it. And your Root's thesis will contain most of the details on how this thing and finally it works out. Okay, so we introduced this new element, and it has its own new, this is a new incentive, right? That's the incentive for assuming systematic risk. And this is the new flow, that's the rate at which you diversify. And then we can just put that in a bigger system. And we went ahead and did that. This is Beer's model with your Root's thing built in, right? So you guys recognize this. These are the banks, these are households, these are the firms. Yeah? This is the good market. And what we've done here is add a financial market. Yeah, well, sitting right here. It has two sub-markets. There's the stock market or securities market and the bond market. The bond market is down there. And the financial markets have the real securities, and then it has to diversify among possible securities, and that is risk market right here. So here you'll see the CR element that's sitting over there, that capacitor. Okay, that allows us to measure the temperature on this thing with this voltmeter here, and there you can see it. Okay, so the thing starts off with very low temperature, meaning it's more or less risk off. That's just the initial condition. And then you see the risk temperament rising until it plateaus at this point. Okay? Then he introduces a shock in the bond market, and the coupon rate goes down. Okay, so bonds are less attractive. And when you see, people are willing to take more risk, right? So the flow of risk is going to increase, right? So that's this flow. Yeah, this increases. And the risk temperament rises again to find a new appropriate equilibrium. So very nice situation. Okay, so that's the deterministic part of the friction, how it gets done. And then you can look at the fluctuations. So you'll see that's the stuff that's coming back, right? So that's Einstein's theory, how this thing is fluctuating. So that's his neg entropy here. So you see the security markets, you see how it, when the bond rate goes down, the coupon rate goes down, you all of a sudden you see a huge flow into the stock market. Okay, the flow levels up. But you see, in the beginning, people are pretty cool, so there are very little fluctuations. And here you see already that the temperature has plateaued at a higher level, so the volatility goes up. Okay, now it goes even higher, so the volatility is even higher here. Okay, so you see this thing actually works. So we're able to calculate these fluctuations based on this model we have for this risk temperament, which is just in this, which is in the C element, which is governed by its heat capacity, right? Now, the other thing that's cool about this solution that you'll never be able to do with your stochastic differential equation is you can see how all these fluctuations percolate through to the rest of the market. So here you go to the households, and you can see that these fluctuations in the stock market, that's all that risk, affect their savings. That makes some sense, right? Because you distribute your assets between stocks, bonds, and regular savings, okay? So you'll have to react in some way to this, okay? But it does very little only to your checking accounts, the current deposits. That makes also sense because the incentive for holding the deposits is not for saving. You don't get any interest anyway. It's for transactional convenience, that you can pay your bills and that you can receive your salary. So you just need that account for way other purposes. It's only in the very extreme cases that you're going to withdraw some from there in order to, to take a little bit less transactional convenience because you can just think you can make so much more money, okay? So that makes sense. You also see here about the firms, their investment behavior, it doesn't really get affected very much by these fluctuations. Also makes sense because their investment decisions are always quite long term, right? And instead, they'll look more about here's an aggregate production shock, you might have from a tariff or something. And what happens here is that they'll have to invest a lot more based on this, and as you see this big wiggle, it totally dominates anything on the stock market, okay? And in the goods and services market, you hardly see anything back. I mean, the average consumer is totally disconnected from the risk in the stock market in these kind of fluctuations. So you see how, before I move on, this approach, of course, this is a very simple equation. Now we've added all kinds of stuff, okay? Now this is a super complicated model, right? It just works, now. You're going to kind of figure out what's going on. And then one way to think of this is to say, all right, you may have more than one sort of fluctuations. This model has one. So you will be able to change this a little bit. Also, this will change in time, but only as the temperature here, or the risk temperature, is a function of time, which it is, because you see the thing going risk on and risk off depending on what happens in the bond market, for instance. All right? So you can bring back this dependence on time here. Now, this drift thing, the way I like to look at it, that's everything else. That's all these things. So that's just the deterministic part of the model. Right? Now, I want to know if these things are all fitted to data in finance. I want to know how you're going to fit this thing to data if you have this model. How are you going to fit this to data? You can't. And it's like taking your smartphone or whatever and thinking you can design that by fitting it to data. You can't. It's just too complex because all these things will all get averaged out. Okay, so there's no hope, I feel, when you're just calculating these parameters with data. You need to have this model, have a clear model about what this mu term does, and you need a clear model about how that sigma goes with temperature. You have to do your thermodynamics. On this way, okay, you have a fighting chance. All right. Okay, so this is just how you can do it, and I think it's a very nice result. I mean, it's totally, it's quite different, and it might be very powerful. It allows us to integrate stochastic behavior, randomness, and all of this. It doesn't only have to be in the stock market; it could be anywhere. Where you have this kind of risk taking, any risk taking. Okay, so that's the first part of the talk. Now I'd like to go to the second part and explain to you what this all has to do with Black-Scholes. Okay, and maybe we should take a short break. Yeah, let's do that. We'll just put this on a short break. Yeah, and then we'll do the other part. All right. Doet die microfoon het? Ja. Okay, we'll go for the second part of the talk. What has all of this got to do with the way they value securities in finance? One of the big highlights of finance has been the Black-Scholes equation. And this one I just copied from Wikipedia. And here it is. And the Wikipedia article actually nicely organizes it into a part that they say is the risky part, and the part that is not risky. So I just call that the riskiest part. They shuffle it around a little bit. So for those in the know, this is, I think, the theta. This they call gamma. And here's some delta here. You have all these option Greeks. Okay. This is a Black-Scholes model, but actually, for theoretical purposes, you can see this S squared here and this S. This is the underlying. That's just a change of variables from the Bachelier model, right? So I'm just going to get rid of it. And what is in black is the Bachelier model. So if you go to log variables, these things just disappear, right? So I take the derivative of the log of S. I'm going to get this stupid S. All right. So I don't consider that essential. It's just going to follow up the reasoning. So that's why I've graded out. Okay, so instead of Black-Scholes, this is the geometric Brownian motion. Bachelier, he was one of the first to do it. He just had regular motion. So the basic idea is the same. Okay. So what we did then is we took spring mass damper system. A lot of work was done. Part of it by Emil at the time, and part of it was continued to write down the Hamilton-Jacobi equation that corresponds to it. Okay, now, here's the Hamilton-Jacobi equation that corresponds to it. This term you recognize, that's the normal term for the energy. That's what the option guys call the theta, right? This is the mechanical action. You take that first derivative. This is the potential energy. This is the momentum squared. And then they add something in for the kinetic, the kinetic energy, this potential energy, and then you might have some other. Right? Then Emil's work allowed us to add this thing in, right? Dissipation. This here is the discount rate, which is the same as the damping rate. Okay. And then this thing got added in. These two terms, they got added in to deal with these fluctuations. All right. This term here has got a second derivative in terms of, I kind of forgot to deal with this. I wanted to replace this by x, this x squared. X. So what I did, we now have this flow, and we have the fluctuations on the flow. Fluctuations go in the other direction. That's just the sign choice of how it was done by Langevin. So we have some kind of net flow, which is the total flow minus the fluctuations. To get the position, we integrate over time. We get this x. You can integrate separately. Then this will be your old cube. And this is something that we've been exploring side, but I kind of want to sidestep that little thing. Okay. All right. Right. So if we do that, we can just replace all these with x, all right? This s here, which is the underlying, then just becomes this s, which is just the stock. But it's got this little fluctuating component built in, okay? So if you do that, you see that this thing corresponds to that. This one doesn't correspond to anything. It's an extra, okay? The other thing you see, what is this price here? What's the price of the auction? Well, if you look at the Hamilton-Jacobi equation, you will see you have no choice but to think of that as the action, the mechanical action, right? That's just the total cost that you make if you go along a certain path, okay? There's no choice. That's just what it is. And that makes sense because this V is something you want to maximize, the value of your option will minimize whatever you chose, all right? And the action is the same thing that something minimizes or maximizes. It turns out there's a minus sign we get in front of this, all right? Now, the other thing you'll see is that these terms, they contain an S-tilde. So the problem with this S is it just covers the deterministic part. That's how we know it. I love it. This is Lagrangian mechanics. It's only for deterministic things. So what we've done is we added a sort of a random Lagrangian that generates appropriately these fluctuations. It's not that hard, but you still got to do it. So here you see kind of a kinetic energy term that belongs to the fluctuation. So these fluctuations, they're coming in here and here, so they have their own power that they're delivering to the mass. So you got to account for that. So you see that, and here you see another term that depends on this thing that's called h bar. In physics, this is called Planck's constant. For us, it takes the role of a little area of phase space. It's just a unit of phase space. And our phase space is the price quantity plane. So this is just the choice of unit of value, right? It could be a dollar or a euro. In general, that's called a notional, right? So if you buy bonds, the notional is $10,000, I believe. If you buy stock, they go at a par value, right? So they may be issued at par, and this will be the notional. So you're saying the stock is trading at 50 times par. So you measure everything in terms of this notional, all right? Huh? And if you do regular transactions in the grocery store, it's like 5 cents, I believe, right? Everything, you can't go lower than 5 cents, okay? So this is another way of seeing it at a notional, right? Okay. So this is the part that is called gamma, and that is usually associated with the fluctuation. And what we see here, it is related to quantum uncertainty. So the problem you have when you buy stuff and you have a relatively high notional, I don't know if 5 cents is high, there'll be transactions for below that, for a cent or something, or 2 cents. It's hard to see how much was the price and how much was the quantity. All you know is that the whole thing was 5 cents, and you can't divide it up further. So there is that uncertainty, okay? And that is apparently this gamma. So it's a different interpretation than sigma that we're looking for, okay? But it's there nevertheless. It's something that they don't consider. The interpretation for sigma is actually in this quadratic term. You can say, well, it's a little hard to see here. We'll see later how it becomes easier to see. And you can say, well, how can it be? This is like a second derivative, and this is a quadratic. And you'll see later that, you can turn the second derivative into square quite easily. You all know how to do that, right? So if you take a Laplace transform, and you have a second derivative, you have this s coming down twice, and you get s squared, right? So it has to do with the exponential function. We'll see this later, all right? So this is really the right analog to this term here. This is a real gamma term in actuals, okay? This is an extra term that corrects the gamma for uncertainties due to the way you're measuring them. All right. So you just got to believe me on this. The way you can clean this whole equation up is by letting this be a complex number, and then you can just put s here and all that. But that's just something, and it's something we'll see later. Okay. So let me see what my next slide is. Okay. So there you are. What's the story? Okay, so I just explained how this goes. You don't know the details, but nevertheless, what's the deal? Well, the deal is that if you have a model like this, it's going to be a bear to do it, but in principle, there must be some Hamilton-Jacobi equation that governs this, okay? There's some kind of Lagrangian description. I mean, you just calculate the action, and then you got to set this. Well, nobody would ever do this in their right mind, but you'll get this totally nonlinear differential equation, which is the Hamilton-Jacobi equation. So you can figure out what really be the black holes. You can do it. It's not that interesting, actually, in terms of this is a very simple first-order system. Much more you can't squeeze out of it. Okay, and even that, it lacks the kinetic energy term effectively. It doesn't really, black holes doesn't really keep track of demand and supply, If there's more demand, it doesn't really do that. The other thing it doesn't do is deal well in credit cycles, because what happens in the credit cycles, in a credit crisis, there's a real need for something, right? So a short squeeze, you get people really wanting this, independent of this, because the inventories are low, so that will be governed by this potential energy term. Right? You see, black holes can't deal with that either. Right? So it's actually, if you look from this perspective, it's pretty limited and pretty clear how you can use this to, something like this would would be an immense improvement. So I believe practically it's better to just first build this, and if you really want to know what the action is and these derivatives are, you just do an integration in Python, and then you can calculate these derivatives if you feel like. You know, you can calculate these actions, these total costs. You have to integrate, I don't know, 1, 2, twice or something. But it's all doable, and then you can find out what you can just see what it does. But I don't think going from Hamilton-Jacobi to LTI models is the right way to go. You set up your LTI model and you engineer back until what this should be. All right. So what's my point here? Well, it's consistent, because one of the problems is like, and they do that right in finance. They show how the stochastic equation leads on the right assumptions if you have a thing to Black-Scholes. But this just shows you that you can use the Hamilton-Jacobi theory to do exactly the same, as long as you adopt the equation of motion approach. Okay? So that's the upshot, yeah. And you get some extra terms for free. It's pretty interesting. Okay? Now you say to yourself, well, I'm still not satisfied with this because this looks hideously complicated. I have this weird thing. This thing has to be a square instead of a second derivative. I have this thing here. I have this one I can go to 0 by getting that thing. I'm not satisfied. And you could say the same thing about Hamilton-Jacobi theory. People were not satisfied with it. And this had limitations in terms of quantum mechanics and things like that. So we can take a quantum mechanical. That's what I want to do now. Quantum mechanics doesn't deal with position and momentum. It doesn't even deal. It deals only with the action, and then it takes an exponential of this action and calls that something that's called a wave function. Okay? It's all pretty mysterious. Why would you have this wave function? All right, nobody really knows. Nobody can give you an answer. Most of it was set up by a mathematician, John von Neumann. And he was a brilliant mathematician, but he just saw how this mathematical structure worked, and that's how they came to it. Nobody really has given to me a really intuitive explanation of what this wave function is. So what I want to do is change that for economic engineering. So we all know what this thing is. This is the total cost if you take a particular path. Okay? Now, what is that total cost? Well, you look at your running cost and you keep adding it up, right? Now, this adding of costs as you go over a path is a problem because there's one problem. Why is that a problem? Because you also want to use addition to add different later outcomes. So you want to use the addition operator too many times. Now, in utility theory, they actually never do that. They do something that's called the solve the decision problem for life. So you say, I'm here, and at the end of this period, I want to be there. And how do I decide on the best thing to do? Well, I just solve in one shot for that whole thing. I can't go a little step by step. There's no way to do that. And then Savage, who is one of the founders of decision theory, called that the decision problem of life. So it's just you go for a long period and you don't prescribe what the individual steps are that you should take to get there. And you don't assume that different paths can lead to different things. You just assume you can grandly optimize this whole thing in one shot, okay? And then if you do all these different things, you want to look at the expectation that is over this. So here's where you stand. You want to go here. You ignore all of this, and you just want to see what this is. Now, you're not sure if you'll end up here, 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 and you're going to add all those up, okay? And you multiply that by some probability. That's what they do, all right? So you want to do addition over the final outcomes. The problem is we already use the addition operator because we're adding up over little steps here. You can't do both. All right? So we need two operators. We need an algebra. What we really want to do is multiply here and then add over here, right? So this is the way it works in practice. If you have a portfolio, the total return is the sum of all the returns of the different stocks and the outcome. But while you're getting the return, while you're returning, you've got to compound them. You can't add the returns. You've got to compound them. This, that, and that. So you start multiplying. You can add the log returns, but you start multiplying, right? So you multiply as you go on here. So multiplying, okay, and then you add when you're there, okay? That's the first thing why you need to do that. Now, we all know that addition can be turned to multiplication using the exponential function. So that's one reason to do that. Okay? Then you see this little I here. So I is the question cool from an economic point of view. So here you'll see something without an I. That's the fluctuations. And say, okay, great. Actually, the exponential function comes out well because this is what we know in finance as the exponential utility. So these are just the net costs associated with it. And that doesn't, just because it's a cost doesn't mean that that's also how much it's worth to you, right? So what you would do is you say there has to be a utility for all of this, right? And the typical utility function that's used is the exponential utility, all right? So this part, at least, you'll know, we're doing okay, all right? Another interesting thing on that part is that now I have two parts. I have this fluctuation, this randomness, but also this determinism that I put with a little I there, okay? So if I take away this part, I'll just get this phase here, okay? 2 minus sign, and I get this phase here. Now, what does that represent? Well, as you know, if you take the power to an imaginary number, you get a circle. You get the action of the circle group. Okay? So this is kind of a rolling action, right? You roll along. So what you're doing is you're counting revolutions. So this is almost like it's your turnover. So you take so many costs you've made, you divide it by your notional, and then you say how many times I've turned over the notional, and you multiply by some other factor. This is a discount factor. And then you do the I there to get the rolling action. Now, rolling in Latin is volvare. So what this means is you're describing utility as it evolves, right? So this is literally evolve. Right? Okay. So the deterministic part, we see it as just evolving in time. Okay. And this part is that's the phase part, and then the magnitude part, actually that's the fluctuation part. Now, what's interesting of the wave function is that if you look at the square of this thing, that's what is interpreted in quantum mechanics actually as the probability. Okay? So we see that what we've achieved here, we've really put literally the probabilistic part, the square root of it, on the magnitude of this guy, right, with the exponential utility. So if I take the log, I get log probabilities, okay? Then I get this thing back. So this is just the log probability, which is also just the units. And I put the deterministic part on the phase. And I have to look at the square root because somehow the way I get there is going to be important for how, this influences this. That's the problem. So you can't just factor it out. And literally just only look at this, forget about your phase. All right? So this is a really interesting way to look at these wave functions and why you need them, and how this interpretation of probabilistic comes out from the random component, the fluctuating component, and how this phase component, really, the use of this I is not totally accidental. It just means that in our minds, we are compounding the utility rather than adding it, okay, as we go in time, and we add it over space, all right? So what we do is we look at the action as the crest of a wave that is kind of rolling like that, and we count the wave crest, and the rate at which these wave crests are going here, that is how this is accumulating in time, just like it would for any. This thing here, this amplitude, gives you the damping of the wave, just the amplitude. So this is another way using utility to capture this entire process in a very convenient and short and concise, this is almost the same, but compelling way also. So this is the utility. This is what I would say is the utility. But the utility is a complex number. It has a magnitude and a phase. The deterministic part is on the phase, and the probabilistic part up. Okay? That's the standard choice. Now you can say, all right, how is this utility evolving then? Now, quantum mechanics have an equation for that, like how this thing evolves over time. So you can see this thing is like a wave. It depends both on time and on where you are, what your stock is. Right? Okay. That thing is called the Schrodinger equation. Here it is. So the Schrodinger equation is way simpler. This is the Schrodinger equation that belongs to this terrible Hamilton-Jacobi equation. This guy here. So if you take this side and you plug it in here, you're going to get that. All right? You actually get a real equation, and that's what we have. You also get an imaginary equation. You can use that to see how the probability flows. But yeah, I haven't discussed this. So you see, this is a beautiful, very concise, easy to understand description. Actually, as this is for a mass spring damper system. You see that the split between risky and riskless is not so clear here, because risk and risklessness is built into one thing. But you do get a nice split between the time dependence and the stock dependence. Okay, the stock dependence goes with the square, so that it's got that's where all the gamma is, and the time dependence is the theta. But it's a more complicated equation because it's got an I here. These are all complex numbers. So if you work it out, you'll see that this thing actually has a gamma, but it also has tons of delta and all kinds of other things. Okay. Now this one is a little bit more subtle. Not only gives you your regular changes in the time value of your option, but it also says something about how the probabilities change. Okay. So it's really a beautiful equation that contains all your information on steroids. Still, this is simple second order system. And if you want to have I think you'll have a tough time setting up a Schrodinger equation, because first, the Schrodinger equation will be okay, but how are you going to determine this thing? It's, this is the simplest equation ever. Fine. Okay. So you'll still be stuck. All right.
Yeah, the V is still the option price.
No. This is a confusion. So let's go back to this slide. There's two V's. Yeah, this is unavoidable. There's two V's. This V turns into an S, script S. Okay? And this V comes out of nowhere because they don't have it. That's the potential energy. All right? Okay? So that's just the confusion. That's unfortunate. See, this S is the underlying, but it's also the entropy. All right? If you go here. What is it? Huh? What was it? I decided to let it in. Okay?
Okay.
Because they always write it like that. If I would write it differently, and we always use V for potential energy, write it differently, that would be confusing. If I sometimes put U, but then I have utility, right? And what I've done in general is when I do economic engineering, I just use, mechanical terminology. And then when I do finance, I just use this. I don't attempt to rewrite it. So, but thanks for the question. Okay. Yeah, you gotta keep your head screwed all right for all this. You gotta keep your alertness up for all this business. And especially when you're trying to combine your different fields, you find out that script S is mechanical action, and regular S is the entropy. Big T is the time period, but it's also a temperature, now. And sometimes I try to be very particular about it and use theta for temperature or something. But it sucks because then theta is the, is also the theta here. Always at some point, it's we're engineers anyway, Huh? Like, well, just yeah, to deal with it. No, we don't have issues. So in a sense, this is for me, a sort of return to what my PhD thesis was about. Because the dynamics of utility was just something that was always a problem. We had some kind of dynamics in probability. We had basis theory, but it wasn't a differential equation in time either. There's all these events coming in, but you couldn't, there was no time. And this thing, this way of looking at it deals with that. And it also tells you what the problem is, that we were always looking at additive utility functions. And they're still there, but you can also multiply them. It's like compounding utility. One thing compounds on this, like evolving utility, and that just has to multiply. Why do returns multiply? You first 5%, and then so you have to multiply it. Now it's just the action of the. Then you take the log, and then back. But then if you take the log of an addition, you don't get anything useful. So you can only do it quickly, only for the, to get the multiplication part sorted out and get your total phase, and then you like plop it back up again. Okay. Right. So this leads me to the last slide before I resume everything. It's like there's another step you can make. Like, where does this Schrodinger equation come from? Schrodinger actually didn't know. He just wrote it down, and he says this works. And they figured out it worked. And nobody really knew why this worked. And then Feynman is the one acting on a tip by Dirac, who appropriately generalized it. So, see, the other thing is this didn't work with relativity. It wasn't relativistically correct. Because I'll tell you why, because time is in it. And you don't know what time is in relativity theory. It can be anything depending on speed, right? Whose time? Right? This is clock time, and you need proper time, right? And space is in here, and so you see this thing is not going to work. So you need a different formulation, and this is called the Feynman path integral. And here it is. So in the Feynman path integral, you say, well, so what's going on? Why does the Schrödinger equation do this? Okay, so remember, for us, the Schrödinger equation gives us the evolution of the utility. How is the expected utility changing? It's a differential equation for the utility. It's sort of the utility dynamics, comparable to how an equation of motion is the dynamics of momentum and of price, yeah, and the Hogan Jacobi is the dynamics of the surplus. This is the dynamics of the utility. Okay, it's a very simple equation, linear in time, not even second order time derivative, right? Very limited. No? Well, why is it correct? Okay, and I think this question was answered by Feynman, saying, well, here's what's going on. So what's happening is, and I'm going to say it now economically, you're standing here at A, so that's your stocks, your position, and you want to go here, all right? And you don't know what you're going to do in between, So suppose I'm looking at you, I have no idea what you're going to do. This is the optimal path, okay? This is when you do all these things. But you're doing all kinds of crazy stuff, So there's all kinds of this, all the time you do that. So nobody knows how you got there, really. You got all these different paths, That's where that randomness is coming from. That would be your answer. Okay. So Feynman says, well, why don't I just, instead of just looking at this total utility over one particular path, that is, or the optimal path, why don't I just average on all? So these are all paths. So this is a ginormous integral, right? So you're not integrating between positions. It's not the path integral that you go, no, you imagine the space of all these paths. It's a huge space. It's a function space. It's infinite dimensional, hyper infinite, and you're integrating over this thing. Okay, that's a funky D here. All right. He was able to figure it out that he was like looking at different slices and doing that. And then later people realized Wiener, whose portrait is hanging here, had already figured it out mathematically for real values here. And then they would do something called a Wick rotation, that they get rid of this I. Anyway, that's just how you would calculate that. So this is what they call a propagator. It just says some kind of overall utility of you getting from there to there if I account for all the crazy curlicues and strange stuff that you may do. All right. If that is that Feynman says that's what's really happening. Okay. So it's almost like if I look at this big market, you got all kinds of crazy people, right? Doing all kinds of crazy things. But somehow these people all start canceling each other out because this guy does something crazy there, but the other guy does something crazy the other thing. So there's a complicated argument to show that what they're doing is just ended up canceling each other out. And then effectively, if you have enough players, you see this thing just going and doing the optimal thing, which you would calculate, following the Euler-Lagrange equation, or doing that things. And if you add randomness, what's happening is that all these paths that are very far away, they get hit down, because if this thing is big, you'll see this e to the minus, So the randomness also gets, and you end up with a lot of players in a path, around here. You don't really know where you are, but effectively, when they're not goods, and the other things, you're just going to end up. Yeah, that's what we're going to show. All right. Now, this is over a whole path, and Feynman was able to show that if you look at a very small a, and this is a plus some epsilon, then you get the Schrödinger equation. We're not going to try to do this. Okay? So this is the big integral, and this is very attractive, of course, from a financial point. because there's this idea like, how can this market be so rational, right? If I look, I only see idiots doing crazy stuff, and yet the market is rational. Yet the law of demand seems to apply, even if there's individuals totally violating it. You see, if you take this point of view, what's happening is all the crazy people just end up canceling each other out. And then on the whole, the thing is hyper rational because the really irrational ones, they die anyway because they lose all their money. But what is irrational? Nobody knows. I happen to want this, but somebody else happens to want the opposite, and they all start canceling each other out, But to make money out of the market, you have to assume it's inefficient. That gets hard when the market is very, very competitive. I think it's the word economists use. All right. So for me, although this looks really abstract and complicated, this is kind of the most compelling picture of why all this other stuff, seems to work. I mean, well, why even this seems to work? Why even this just works? All right. So that ends the theoretical development. In the presentation, I had another slide where I showed what we do with it. So now we build all this stuff in here, right? So we'll have a system here. We can make a big model, as what I showed you. You're going to see this will be for a portfolio or a stock market or anything, And then this thing is what we call a dynamical systems model. And in business, that's called an organizational digital twin. I love abbreviating things in business, ODT. It is. That's a nice way of looking at it. All right. Of course, we have all these disturbances, all these things. So maybe you want to do disturbance rejection, maybe you want to steer the system. So what we would do as engineers, we would say, well, this is some kind of system, the plant, some process, and we just use process control. So put some controller here, PI controller, PID controller. Here's some observer, some sensor. This is some supervisory controller, whatever. Now, if you take this engineering process control and replace engineering with business, leave process, and replace the control with management, you get a field called business process management. That actually is a big field, okay? BPM, they abbreviate everything. So, what's the big picture here? Well, the big picture is that with our methods of using dynamical systems to do Black-Scholes type of stuff or any type of valuation, we can integrate that into our dynamical systems model. That thing serves as the digital twin that you're going to have if you're running a brokerage firm or your energy market or whatever it is you do. Right? Once you have it in there, you're not just saying, hey, that's great. I mean, I can model this and it fits, No, you can say, no, I want to control things. I want to achieve my objectives. And that's another great advantage of this type of solution over Black-Scholes or anything else you might come up with. Well, what's that to control? These things you can control. Maybe we can reduce the fluctuations. Maybe we can do all kinds of other things. Okay, so that's the upshot. And so I think I'm going to leave it at that. All right. So unless there are questions, then we can stop the recording.